What if you could test drive the future? Run an experiment on a huge idea without any of the real world risk? Well, that's pretty much what we're diving into today with modeling and simulation. It's the science of building these incredible virtual worlds to understand and, yeah, even predict our real one. So let's get into it.
Okay, so let's kick things off with a big question. How in the world do you run an experiment on something that seems completely impossible to test?
I mean, just think about it. Testing a brand new aircraft design while it's in the air, that's wildly dangerous. Messing around with the live stock market, you could literally wreck the economy. And it's not like we can just pop over to a distant star to run a few tests. These systems are way too expensive, way too risky, or they're just physically out of our reach. So how do we study them? This is the exact problem that modeling was born to solve.
But before we can even think about building a virtual copy of something, we first have to learn to see it in a whole new way. We have to be able to break it down and understand it as a system.
Okay, so here's the formal definition. And really, the two key words you need to focus on are collection and interact. See, a system isn't just a random pile of parts. No, it's a network, a web of components that all influence each other to achieve some kind of goal.
All right, to make this super clear, let's use an example we all know. Something from everyday life, a simple bank. So let's break down this bank as a system. The entities, those are the main objects we care about, right? The customers. Those customers have attributes, properties like their account balance. They perform activities, which are processes that take time, like making a deposit. And then you have events. These are the moments that change the state of the system, like a new customer walking in the door, which instantly makes the line one person longer.
And what's so cool is that this way of thinking, it applies to, well, almost anything. For our solar system, the state of things is defined by the position and velocity of the planets. For a financial market, it's all about interest rates and stock prices. For the weather, you're looking at things like air temperature and atmospheric pressure. All these huge, complex worlds can be understood as systems with states you can actually measure. Now, systems also tend to fall into two main categories. You have a discrete system where things change in distinct steps. Think about that line at the bank. The number of people jumps from 4 to 5 in an instant. Then you have a continuous system where things change smoothly over time, like the water level in a dam slowly and steadily rising. Getting this difference is really key for what comes next.
All right, so we've got a handle on what a system is. The next logical question is, how do we actually make a copy of one so we can study it safely on a computer? And this is where we build a model. And listen, this is probably the most important thing to get your head around. A model is a purposeful simplification of reality. It is not a perfect clone. We have to strip away all the extra noise and focus only on the parts that are essential for the question we're trying to answer.
And simulation? Well, that's what happens when we hit the play button on our model. We're bringing that simplified system to life, letting it run on a computer so we can watch how it behaves and changes over time. Now, you gotta understand, model isn't a one-size-fits-all thing. Just like a good mechanic has a whole toolbox full of different wrenches and screwdrivers, a modeler has different types of models. And the trick is choosing the right tool for the job. On the one hand, you have physical models. These are things you can actually see and touch, like a little scale model of an airplane they stick in a wind tunnel. And on the other hand, you've got mathematical models, which use the language of equations and symbols to describe how a system works. It can be something as simple as distance equals rate times time, or something way more complex. Another really big choice is whether your model is deterministic or stochastic. A deterministic model is kind of like a perfect machine. You put in the same inputs, you get the exact same output every single time, predictable. But the real world is messy, right? It's random. A stochastic model embraces that randomness. It has chance built into it, so it gives you a whole range of possible outcomes, not just one single future.
So, how does all this actually happen in the real world? Well, it's not just a bunch of people winging it with some code. There is a serious, step-by-step blueprint that every good simulation study follows.
Everything, and I mean everything, starts with a solid plan. This is phase one. You have to clearly define the problem you're trying to solve. You have to figure out exactly what questions the simulation needs to answer. And this is also where you start sketching out that logical model and gathering the real-world data that's going to fuel the whole thing. Next up, you move into the building and testing phase. This is where you translate your ideas into actual computer code. But here's the thing.
Just because your code runs without crashing doesn't mean you're done. Not even close. This brings us to two of the most critical steps in the entire process: verification and validation. And this is such a key distinction. Verification asks the question, did we build the model right? It's all about the code. Is it free of bugs? Is it doing what we designed it to do? But validation asks a much deeper question. Did we build the right model? In other words, do the results from our simulation actually match what we see in the real world?
And at last, we get to the fun part, the experimenting phase. This is where all that hard work pays off. You carefully design all your what-if scenarios, and then you run the simulations, which generates a ton of data. Then you use statistical tools to analyze that data and find the hidden insights. And the final, absolutely crucial step is to document it all and report your findings to the people who need to make the decisions. Okay, so after all that, this whole rigorous process leads to probably the single biggest, most important idea you should take away from all this.
The famous statistician George Box put it perfectly. All models are wrong, but some are useful. What he meant is that any model, any map, is just a simplification of the real thing. It can't possibly capture every single tiny detail of our infinitely complex reality. And you know what? That's okay. It's not supposed to. So, if you're going to remember just a few things from our chat today, let it be these. Models are incredibly powerful tools for getting our heads around complex systems, but they are always intentional simplifications, not perfect copies. And that means the goal of a model isn't to be perfectly right. The goal is to be useful, to help us understand our world, ask better questions, and at the end of the day, make smarter decisions.
So, I'll leave you with this thought. We've seen that models are basically tools for understanding. If you had this whole toolkit and you could build a model of anything, what part of your world would you want to build a virtual copy of, just to see how it really works?